All right, hey geometry class, this is Mrs. Comature. I'm going to be gone again today because daycare is closed, so I'm staying home with my kiddos. Um, First period class, I think you guys have a little bit left of notes on 12-2, and what is it, sixth period class got done with 12-2, so we should be moving on to 12-3. But I'm going to go ahead and give you the notes for 12-4 because they're easier to explain. I'd rather be there when I explain 12-3. So I'm going to go ahead and do 12-4, and then first period we'll come back and finish 12-2 and 12-3. Sixth period we'll do 12-3 when I come back. So I will be back on Tuesday. And we'll do some catching up then. But I want to get 12-4 done and have you guys do homework for 12-4 so we don't lose another day. So here is 12-4, talking about geometric probability. We started getting into probability in this chapter, and this is kind of having to do with, I don't know, lengths and areas and that type of thing. So the first thing that talks about is if we have like a line segment over here, and this is a pretty easy concept. Let's say this line segment is, I don't know, 20 inches long, or 20 units long. I'm going to put 20U. BC, let's say he is 7 units long. The chances of me putting a point down on this line, let's say it's over here or anywhere else on this line. We know that it's going to land on that line. The chances of me putting a point down on that line and having it land on BC is just 7/20. It's like the area that I'm wanting over the total area. So that was a pretty basic concept. Same thing down here. Point X is chosen at random on JM. Okay, so I'm going to highlight JM here for just a second, if I can. There we go, JM. JM is, if you add these all together, 3, 7, and 4, that's 14 units. So JM is 14 units long, right? We want to know the probability that if I slap a random point down on this line, wherever he's located, I want him to be located on KL. KL is just this little guy right here. Okay, and he is 7 units long. So I have a 7 out of the entire 14 chance of him living on KL, which you can reduce as 1/2. All right. Oops, that's supposed to be a 2. So I have a 1 in 2 chance of any point that I've slapped down on this line, him living in this area versus the rest of it. 1 in 2 chance, okay? So pretty easy stuff. Now they're going to get into area stuff, and basically they're going to say, like, here's your dartboard, right? And my dartboard on the outside is a rectangle, but on the inside I want it to land in B. So they're saying, they'll give you the scenario that, like, hey, if I shoot an arrow and I know it's going to land in this rectangular thing, what is the chances of it actually hitting the circle as opposed to the area outside of here? Okay, so we'll have to know what our areas are for each shape. So let's go ahead and I'm going to go down here on the second page. Flip your page over. And there's some area down here at the bottom. Maybe that we're going to go ahead and put some like circle area and triangle area and rectangle area and that type of thing. Okay, so let's start with rectangle or square. To find the area is length times width, or base times height. So put that down. This is area. Area. This is area of all of these. So length times width or base times height. So this is, let's say this is a rectangle and not a square. 3 by 2, the area would be 6. Okay, that's stuff you should just know. But if you don't, it's written there. Okay, a triangle. The area is base times height. I'm hitting a button here. There we go. Base times height divided by 2. Or some people like to do half base times height. That's the same thing. So base times height divided by 2. The reason why a triangle is that formula is it's the area of a rectangle, but then just split in half. Okay. And then let's go ahead and do circle. I don't know what else we're going to need besides these 3, so let's just leave it at that. Circle. The area of a circle is pi radius squared. Okay, so the radius is just the distance from the center to the outside, so let's say this is 10. Okay, we would take 10 and square it. write out what that looks like. 10 squared. 10 squared is 100, so we have pi times 100, which is just moving the decimal 2 places. So instead of it being 3.14, it's going to be 314 point like 159. 314.159, something like that. Okay, that's what that area would be. So these are the formulas that you're going to need probably in this section. I don't think you need any more than that, but there's those. Okay, so let's go back to first page. Where's my first page? Here we go. Back to first page. Oh shoot, I have a kiddo awake. It's 7:15. All right. Exercise 2. A Chicago Transit Authority train travels or departs a station like Addison. Oh shoot, this is going back to this first one. Sorry, I'm getting ahead of myself. Like Addison on the red line every 15 minutes. Okay, so what I'm going to do is, since the train arrives every 15 minutes, I'm going to go ahead and make a line segment where there's 15 minutes long. Okay, 15 minutes is the length of any train. So I could arrive here where I have to wait 0 minutes for the train, or I could arrive here where one train has just left and I have to wait 15 minutes for the next train. Does that make sense? I have 0 minutes. I could be coming to the station right as the train is coming, which means I have to wait 0 minutes, or I could be coming to the station right as a train is showing up, or right as a train is leaving, which would mean I have to wait 15 minutes for the next train. Okay, so I'm going to do my intervals here. Here is waiting 5 minutes. Here is waiting 10 minutes. Okay, what is the probability that you will have to wait 5 minutes or more for the train? Okay, so since we're mapping out wait time here, waiting 5 minutes or more would be like this entire chunk, right? And that entire chunk is a length of 10 out of 15. Okay, so I have a 10 and 15 chance of having to wait more than 5 minutes. That's this map of this little segment here. And that, if we reduce it, is 2/3. You can kind of see that on the line segment, that 2/3 of the line is what's grouped here. Okay, so there's that. Map out, write your line and mark it so that you can see what portion of it that you're talking about. Okay, so now here's where we're getting down to the area. I skipped example 2, sorry. So example 3, use area to find the geometric probability. Suppose a skydiver must land on a target down below here, so you can kind of see this little target, of 3 concentric circles. That's just 3 circles inside of each other. So red, yellow, blue. If the diameter of the center circle is 2 yards and the circles are spaced 1 yard apart, what is the probability that the skydiver will land in the center circle? Well, that's a lot of confusion. So I'm going to go ahead and I'm going to go over here. I'm going to map out what this thing looks like. Maybe, if I can. Here's my outer circle. Then I have another one inside of that. Please let me draw it nicely. Okay, that's not terrible. And then there's one on the inside. Okay, so this is my little map here. The center circle is 2 yards, and that is in diameter. So from here to here is 2. And then the circles are spaced 1 yard apart. So this guy is 1, and this guy is 1. So we really have to, we're trying to do probability. What is the probability? And so we're going to have basically a total area versus the area that I want. Area want. So I want to land inside of the small circle. So this is going to be small circle, and the total area is going to be the large circle, the one on the very, very outside. Okay, I know that I'm going to land inside of the large circle, but I want to know the chances that I'm going to also land inside of the small circle, because I could land inside of the big circle, but be like over here, right? That's not inside of the small circle where I want to be. So I want to know the chances of me landing in here versus the total. Okay, so equation for a circle is pi radius squared. Okay, so let's do the area of the small circle first. They told me that the diameter was 2, but that's not the radius. The radius of this small circle would just be 1, because we're going from the center to the outside. Okay, so I'm going to go ahead and let's go down here. Area of the small circle would be pi times 1 squared, because that's what my radius is. Okay, pi times 1 squared. All right, now don't multiply that through because we're going to do some magic here in just a second, and we're going to simplify this guy, and he's going to be really super nice. So there's my area of my small circle. Now the area of my large circle would be like the distance from the center to the outside. It would be the distance from here to here, okay? Now this is not 2, this is 1 again. And this is 1, and this is 1. So that large circle has an area, or has a radius of 3, okay? So if we're doing the area of the large circle, we would have pi times 3 squared, okay? And then what's really nice about this is, since there's pi on both the top and the bottom and we didn't multiply him through, he can just cancel. It's like reducing. Okay, so now we only have 1 squared, which is 1, over 3 squared, which is 9. So that means that if I have a circle on the outside, and I know that I'm going to land within that circle, I have a 1 in 9 chance of landing inside of the middle circle rather than landing somewhere out here, okay, where I'm not inside the circle. So 1 out of 9 chances is what my probability is. Okay, so that's just showing you kind of how the geometry works. Make sure you have these equations written down or know them at least, and that will get you through this section. Okay, I will post the homework on the Google Classroom page. Go ahead and do that homework while you're waiting in class here. Yeah, I realize that we haven't done 12.3, and some of you guys aren't done with 12.2, but just stick with me, do 12.4, and then we'll come back in on Tuesday. We'll finish up those middle ones, okay? So look for that on Google Classroom, and that is all I have.